Have you ever really thought about what goes into making a perfectly clear X-ray? It's not as simple as just pointing a machine and hitting a button. It's this amazing mix of physics and technique, a real science. So, let's jump right in and see how radiographers take an invisible beam and turn it into a super detailed, life-saving image.
Okay, so just look at this. On the left, you've got a radiograph that is sharp, it's clear, it's full of detail. It's an incredible tool for doctors. And on the right, well, it's a blurry, washed-out mess. The difference is just night and day, and in a hospital, that can literally be the difference between catching something serious and missing it completely. So what's the big secret here? What is it that separates that perfect, crisp image from a useless blur? Well, it really boils down to getting three things just right: controlling the X-ray beam, nailing the geometry of the shot, and then, of course, perfectly capturing that final image.
Let's start right at the source, the beam itself. Before an X-ray even gets near a patient, its basic properties have to be dialed in perfectly. You can think of these as the essential ingredients in our recipe for the perfect image.
First on the list is kV, which stands for kilovoltage. The easiest way to think about this is as the power or the punch of the X-ray beam. The higher the kV, the more energy each little photon has, which lets it push through denser parts of the body. It's really the force behind the whole thing. And then we have ms, or milliampere seconds. So if kVp is the power of the beam, ms is the amount of X-rays. It controls the sheer quantity of photons being sent out. It's kind of like a faucet. MAS is how wide you open it and for how long. It's all about volume.
All right, now this is where the physics gets really interesting. Distance. Distance is a huge deal. There's this fundamental rule called the inverse square law. And what it basically says is that the farther away you get from the X-ray source, the weaker the beam gets. And believe me, it gets weaker fast. So how fast are we talking? Well, check this out. If you just double the distance from the X-ray tube to the film, the beam's intensity plummets to just 1/4 of what it was. That is a massive, massive drop that radiographers have to compensate for every single time. But there's another major villain in our story, and it's called scatter. You see, as those X-rays travel through the body, some of them don't go straight. They bounce off in all sorts of random directions. This scatter radiation acts like a fog, and it can totally ruin an image by washing out all the important details.
So how do we fight the fog? With a really smart device called a collimator. It's basically a box with lead shutters inside that lets the radiographer trim the beam down, shaping it so it only hits the exact part of the body we need to see. Now, it's really important to get this. It shapes the beam. It doesn't focus it. X-rays can't be focused with a lens. By trimming the beam, you get way less scatter, and that means you get a much, much clearer picture.
Okay, so we've got the beam under control. Now we move on to part 2, the physical setup. At the end of the day, an X-ray is really just a very sophisticated shadow. And because of that, the geometry, how that shadow gets cast, is absolutely everything. You've probably seen an X-ray that looks a bit fuzzy or stretched out, right? So what does that happen? Well, the answer almost always lies in a few simple geometric factors that can either make an image perfectly sharp or turn it into a blurry mess.
The technical term for this blurriness is penumbra, which is just a fancy way of saying the shadow has a fuzzy edge. And it's usually caused by one of three things. The source of the X-rays is too wide, the X-ray tube is too close to the film, or, and this is a big one, the patient is positioned too far away from the film. Any of those will mess up the sharpness.
So what's the takeaway here? It's actually a really simple rule of thumb. To get the sharpest possible image with the least amount of magnification, you want to get the body part you're looking at as close to that film as you possibly can. Short distance, sharp image. It's that simple. And it's important to know there are two different kinds of geometric mistakes. On the right, you have magnification, which just makes the whole shadow bigger than it is in real life, usually because of distance. But on the left, you have distortion. That's different. It actually changes the shape of the object, like making an oval look like a perfect circle. And that happens when the body part isn't lined up parallel with the film. All right, we've dialed in the beam, we've set up the geometry. The final piece of the puzzle is understanding how all that work translates into the blacks, whites, and grays we actually see on the film. And this all comes down to two key ideas: density and contrast. This right here is the heart of it all, seriously. On the left, you see density. That's the overall blackness of the image, and it's controlled by our friend MAs. Not enough MAs, and the image is pale and washed out.
too much, and it's just a black rectangle. Then on the right, we have contrast. That's the number of gray shades you can see, and that's controlled by KV. A low KV gives you high contrast, very stark blacks and whites. A high KV gives you low contrast, with tons of different shades of gray.
This quote on the screen just nails it. If you remember one thing from this, let it be this. The KV controls the number of shades of gray, and the MAs controls how dark those shades are. Getting that relationship right is the real secret to a perfect exposure.
So, when it's all said and done, a radiographer is looking for these 4 things. They want excellent, sharp detail. They need the right overall density, not too light, not too dark. They need the right amount of contrast for what they're looking at, whether it's bone or soft tissue. And of course, they want as little distortion as possible.
See, making a great X-ray isn't about just one setting. It's this constant, skillful balancing act. You change one thing and it affects everything else. So let's put all the pieces together one last time. This chart right here is the ultimate summary. It's the whole game plan. Your KV gives you penetrating power, which sets your contrast. Your MS sets the quantity of X-rays, which controls your density. Your distance, or FFD, messes with the beam's intensity, affecting magnification. And finally, patient position is the key to sharpness and avoiding distortion. Mastering this table, that's the art and science of being a great radiographer.
So the next time you see an X-ray, you'll know about the incredible amount of thought and precision that went into making it. And now that you know the rules of the game, you have to ask yourself, could you spot the flaw in a bad one? Could you tell if the problem was too much power, not enough quantity, or just bad positioning? It's kind of fun to think about, right?